Welcome to the second keynote speech of the day and the third and final keynote speech of the conference. And I'm happy to welcome Dr. Alessandra Gorla from University of Madrid, Spain, IMDEA, for this keynote speech. So before she starts her talk, let me just introduce her briefly. Alessandra is an associate research professor at IMDEA Software Institute, Madrid, Spain. Prior to that, she has been working as a postdoc with Andre Zeller at Software Engineering Chair at Saarland University in Germany. She obtained her PhD in the STAR group led by Mauro Pezzi, pardon me if I get the pronunciation wrong, at University of Lugano in Switzerland. Her research interests are in malware detection for mobile applications, automatic software repair, software testing and analysis. She has published extensively in all the top flagship software engineering conferences like ICSE, ASE, and so on. And we are very happy and fortunate to have Alessandra here. Over to you, Alessandra.
Thank you. Thank you for the invitation. Thank you for being here for my talk. So thanks also for the introduction. I actually prepared at the beginning of my presentation a brief summary of my research that was actually already provided. So today I will be talking about the analysis of mobile applications, and I will try to answer a question that you might have if you work in this domain, or maybe even more if you do not work in this domain. And it's about why is most of our research on Android other than other platforms. So quick introduction about myself. So I'm originally Italian, so that's where I started doing research, even as a bachelor student. So I was very lucky to work with Mauro Pezzi, who has been working on software testing for many years. And so basically when I was in Milan working with him, I started working on software testing as well. So somehow I had, since the very beginning, the idea that the importance of the software quality is extremely important when we develop software. And I was really working on techniques that aim to identify bugs before we ship them to the final users. Then I kind of like research, so I moved on for a PhD. I went to Switzerland, and there I kind of got interested in this idea of automatic repair. So we had a very good talk yesterday from Abik about this. And since this was really the hype topic when I started the PhD, I started looking into this. And basically I was like, okay, even if we try really hard to develop techniques that aim to find bugs during development, no matter how good we are, we end up shipping software with bugs anyway. So can we think of the next step? That is, even if a software component is deployed with some bug, can we think of some techniques that can fix or at least alleviate the effect of these bugs at runtime? So I came up with this idea of automatic workarounds. So the idea of some components that could automatically avoid the failure at runtime. So even if the component was buggy, in the end, it was not really showing the failure to the user, but it was kind of finding a different path to somehow work at runtime. And so this was kind of the topic during my PhD. And then I moved to Germany, to Saarland, working with Andreas Zeller, who many of you may know because of Delta debugging. And when I was there, so I started in 2012, he said, okay, now it's like everything is about mobile applications. It was like the beginning of the development of mobile applications, and there was still not much out there in research, and there were many problems to be solved. So we thought, okay, can we think of techniques that can automatically assess whether a mobile application is trustworthy, so whether it respects the privacy of the user or not. And during this time in Germany, as a postdoc, I also spent a few months in Google, in Mountain View, developing some of the techniques that we have been brainstorming and we have been prototyping in Germany to actually have them applied on the Google Play Store, actually. And after this, I landed in Madrid, where more or less I still work on the same research topics, and I kind of like to define my research interests as follows. So I like to work on testing and analysis techniques. So basically what I have been doing all my research life since the bachelor. And I see two main goals of all the techniques that I use or develop. The first one is to care about software quality, meaning I like to develop techniques that aim to assess that a software component is actually without bugs, and we try to do this with test automation techniques. And the other goal is trustworthiness of software. So how we can use analysis techniques to assess the behavior of a component and assess whether it is okay for a user to use it. So there is no violation of his privacy, for instance. And I like to work on different levels and on different artifacts when we think about different systems. Depending on the context, I like to work on source code, executable code, or as a black box, just using a user interface or an API that allows me to interact with the system and somehow get the behavior. And in terms of systems and domains, I have been working on standalone Java systems, web applications, and mobile. So for the purpose of this talk, I'm actually going to focus on the trustworthiness of software as a goal, focusing mostly on executable code and these domains, like the mobile domains, specifically Android and iOS. But this is basically to say, if you have any interest in anything else that is on this slide, please come and talk to me. I'm happy to discuss this. Okay, so back when we started in Germany, there were a lot of questions about mobile devices and mobile applications. So it was like at the very beginning when developers could actually develop applications to be deployed on Android devices. And as a user, you could have asked, okay, should I really trust this application? Is it malicious? What kind of information does it access? What does this application really do with my data? And should I trust this developer or not? Like if it is shipped by Meta or any known software developer, I may trust it, but what if I don't know the developer? And in the last 10 plus years, we have been developing techniques that can automatically analyze mobile applications, indeed to assess the privacy and security risks of mobile applications. Back when we started, so in 2013, we had one research question that we started to think about. And there were already some data sets of Android applications that contain malware. And back then, malware Android was extremely simple. So it was basically just executing some shell commands on the device to do something harmful for the user on the device. Or they were like sending SMS to premium numbers so that you could basically have the user losing some credit on his balance. But somehow the existing techniques were trying to flag malware as, okay, if an application is sending an SMS, then it's likely to be malware. Because this was actually a very prevalent feature in malware back then. But, I mean, is it really fair to say this? And, I mean, what I started thinking is that, well, I mean, to define what is good and what is bad, it really depends on the type of application you're looking at. So what do you expect from the application to do? And if the application is doing something that you do not expect, then, okay, you should flag it. And just to give you an example, we were looking at this application that was called London Restaurants. That is like a very simple recommendation app for a traveler in London that was basically suggesting you places where to go, depending on your location. So it was suggesting you where to go in terms of restaurants and whatever. Now, from this type of application, you expect that it needs to access the information about your current location because it needs this information in order to work. But the surprising thing is that looking at the actual behavior of the application, you could find out that the application was collecting also some sensitive data from the user that, I mean, it's kind of not clear why they were useful for. So it was even collecting the personal user account information. It was sending out the mobile phone number of the user and was collecting the device ID as a way to identify the device. So this is kind of, to me, even if this application was not sending out SMSs to premium numbers, this behavior was kind of fishy. And because of what I was expecting from this type of app. So a year after, we could actually deploy a first prototype of a technique that we called Shabada, and that we presented at ICSI 2014. And I mean, funny enough, ICSI 2014 was happening here in India, so I know that India brought me very good luck in this line of work, and I'm very happy to be here again 10 years after. So how does this technique work in a nutshell? So we were collecting as many applications we could, both the code of the application and the description in natural language process, natural language of the application that was available on the Google Play Store. Then with the description in English that was stating what the application was doing, we were using some topic modeling, so some natural language technique to group descriptions together in terms of which ones are similar. And then we could use clusters to cluster applications that had similar descriptions. So the idea was, okay, we can somehow group together applications that talk about navigation and applications that talk about, I don't know, messaging and so on. This, in a way, was a much better way to classify applications than what we had back then on the Google Play Store categories. Now, with these clusters, then we started doing some very basic static analysis, and we were looking at what the applications were doing. And we were basically looking at what APIs of the Android application the application was using, and we were reporting outliers. So what was the intuition here? So if we look at a cluster of applications that recommend places where to go, as the case of the London restaurants, we could see that the common behavior of these applications were like to access the current user's location. But very likely none of these applications were sending an SMS. So if you could find within this cluster an application that was sending an SMS, then you could see it as an outlier and you could flag it as an anomaly that should be checked. Instead, if you were looking at a cluster of applications regarding messaging, you could see that the common behavior is about sending SMSs. So this is like not something that you should flag as an anomaly because it's the normal behavior of that cluster. So we continued with this line of work. We have been thinking, how can we improve on the analysis of the application? So in a way, looking at what are the APIs that the application is accessing is a way of modeling the behavior of the application or of the same, the whole cluster. So how can we improve on this way of modeling? And we saw that a much better way of describing the behavior of an application was to look at information flows. So rather than just looking at what type of information the application is accessing, for instance, the application is accessing my list of contacts or is accessing my current location, if I can get the information of how this information is used, so for instance, my current location is logged or it is sent to an external server somewhere to the other side of the world and so on, is a better way of understanding what the application is doing. So we have been using FlowDroid. That is a very popular open source application framework to collect information flows of Android applications. And we have been using this information to model the behavior of an application, again, to distinguish between malware and benign applications. And we had much better results the year after. We continued on this line of work looking at another artifact that's also very common in mobile applications. That is the user interface. Again, following the intuition that we had at the very beginning, that is, the user is kind of has an expectation of what the application is doing. And while at the beginning we were looking at the description in natural language, we could also think of what is the expectation in terms of the user interface. And with this information, then again, you can flag whatever is not really matching the expectation. So just to give you an example, if you have a user interface that looks like this and you have a button that looks like this, then as a user, you expect that by pressing this button, either you see that the camera is opening or you may have access to all the photos on your devices. You do not expect, for instance, that you get access to your list of contacts or you're making a phone call or sending an SMS. So again, we have been developing some techniques that analyze the user interface and see what the application is doing in the background to try to match whether what you see as a user interface actually matches the behavior underlying. Now, all these techniques were actually based on static analysis, but we have also been looking at dynamic analysis frameworks. And back in 2015, we saw that there were already many test input generation tools for Android. So tools that basically allow you to automatically execute, so automatically interact with an Android application installed on a device or on a simulator. And we, developed a framework to try to compare these. And back then there were, I think, already 10 or 15 different frameworks. By now there are many more. We see that actually some of them now work pretty well. But yeah, basically, in a way, the message here is that back then there were already many frameworks that allowed you to dynamically analyze an application. Now, with all these frameworks that we had developed or with, that others developed, we have been doing quite a lot of empirical studies on Android apps. And here, just to mention a couple. So in 2020, we have been doing an empirical study on parental control applications. So parental control apps are applications that many parents install on underage phones to try to control what kids do with their device. So these kind of applications either block specific behavior or block specific applications, or somehow they limit or at least they trace what the application is doing. So to check what kind of phone numbers the kid is calling, what kind of websites the kid is browsing to, and so on. So with our frameworks, we could statically and dynamically analyze roughly almost 50 applications from 43 well-known developers with many installations. And we could see that there were actually serious privacy issues with these applications. So some of these applications were sending personal information on the network without properly protecting the information. So the information was sent in HTTP rather than in HTTPS. So it was actually easy to get personal information of underage users by just listening to the network traffic. Some of these applications, actually a third of these applications, could send personal information without proper authorization of the user. Now, the European law is very clear about this thing. The user needs to agree before some personal information is collected. So there needs to be a specific approval. And a third of these applications were actually not doing this. So they were collecting the information without this. And if I recall correctly, over 70% of the applications that we analyzed actually share private information from underage user with third parties without mentioning the presence of these third parties in their privacy policies. Again, this is very worrying because you know that there are some third-party components, including the applications, that have access to this personal information, and the application is not, developers are just not mentioning this fact. Another study that we did was regarding how Android had been changing the permission system with Android 6. Now, if you recall, Android used to have a way of accepting all the permissions when you were installing the app at the very beginning. Otherwise, you couldn't install the application at all. And with Android 6, they actually changed this model to what is called a runtime permission model. That is, now the user is asked about whether is okay with granting a specific permission when the permission is used the first time. Now, with this major change, Android also introduced the concept of groups of permissions. So rather than asking, okay, do you want to grant permission to read your list of contact, and then do you want to grant the permission about writing on your list of contact, meaning whether you want to grant the application to just read or to edit your contact list, they actually grouped some of these permissions to make it more usable for the user. Now the thing is, with these groups, once the user was granting permission to one of the permission in this group, then all the permissions in the group were granted in the current and future releases. So what we have been wondering is, can some of the Android applications take advantage of this? Meaning, maybe at the beginning they ask for like a not so worrying permission, and then later on, once the user already agreed on having access to this permission group, then they also ask for other permissions in the same group, and they might do something that is a little bit worrying. And the answer is yes. So we have been analyzing over 3 million applications that we could download from the Google Play Store. So this was a huge empirical study. And we saw that, and we downloaded as many versions as we could from the same application to see how the permission, the list of requested permissions was changing. And we saw that around 10% of the applications were actually doing this. So they were asking for more, at least one more permission that was automatically granted because another permission in the same group was already there. Then we looked a little bit more into this, and we found many worrying cases, and here I'm just covering two. So this application, the touch poll keyboard application was one of the many available keywords that you could install on your device. So it was like a keyboard with some extra features that the user might want it to have on its device. Now, in order to work, then the application was asking permission about the phone state. That is, whether the phone was in a state, for instance, in a phone call or not. And in that case, the keyboard was probably disappearing or something. So it sounded like fine to grant the permission, this kind of permission to this application. But later on, after a few releases, the application was actually getting the list of phone calls that used to belong to the same group and was sending this information to, I think, a Chinese server. Again, so this change was happening without any notice for the user and without the user granting any extra permission. And we could really see it, we could prove it. Now, this application is no longer on the Google Play Store. The first one had a similar issues. So the first one is an application that was supposed to block specific phone calls. So, I mean, clearly this application, because of what it promised, needed to have access to the list of contacts, because you could allow to say, okay, I want to block phone calls from this specific user. And again, with the same trick of belonging to the same permission group, after a while, what the application was doing was to asking, and it would have been granted without any further confirmation of the user, the list of accounts from the user himself. And specifically what the application was doing was looking for email addresses of specific domains, if I recall correctly, specifically on Outlook and Gmail, was encrypting this information and again sending this to their server. Now, why this application should be doing this? Well, this kind of a fishy behavior, and in fact, this application was also removed from the Google Play. Now, a long list of things that I've been doing, and you might just wonder, okay, Android, Android, Android. So why does she keep talking about Android? Android clearly is not the only mobile platform out there. There is at least iOS that is, may not be as popular as Android in terms of total number of users, but actually has a very significant segment of the population, especially in the US and Europe. So why did I do most of my research on Android? Well, personally, because since the very beginning of my career, I have been using a very popular framework that is called Suite that allows you to analyze Java bytecode. And what the authors of Suite did at some point was to extend Suite to also analyze Dalvik bytecode. That is what you have on Android application. That is actually quite similar to Java bytecode. So I knew the framework. The framework is amazing. It allows you to develop any static analysis in just a matter of hours or days because most of the infrastructure is already there. And what I could also see back in 2015 is that there were many tools that allowed you to play with applications, Android applications, so you could easily dynamically analyze applications. So basically for me it was like, okay, I have all the tools, I have all the knowledge, so let's go for it. But actually, so what I tried to do was look for papers in the software engineering area in the last 10 years that contain the word Android, and I could find over 2,000 papers. And I did the same for using the keyword iOS, and I could find less than 200 papers. So, I thought, okay, probably most researchers have been thinking the same way that I've been thinking. That is, okay, let's start with Android just because all the tools are already out there for me to do some basic analysis. So it seems like a very nice platform to start with. However, I got to a point after, well, almost 10 years that I said, okay, there are so many things already on Android that we should start looking at something else. And especially when I saw this, I really saw an opportunity. I said, okay, everyone has been working on Android and even trying to develop the same techniques for iOS, is interesting, is a contribution. So let me try to switch to the other platform, the other popular platform on mobile, that is iOS. And I was aware that the tooling for iOS was not really there. And that's why I said, okay, let's start working on a very simple problem on mobile application. That is, let's try to identify, given a mobile app, what are the third-party libraries that are included in this application. So this has been done already a lot in Android. I think I can name at least 20 papers with different techniques that are better and better and do different things on Android. And I could find only one paper that was kind of doing this for iOS, but had lots of limitations. So basically, there was nothing. So why, we said, okay, why starting with this simple problem? Well, even if this is a simple problem, is actually very important. Well, because, I mean, the idea of saying, okay, I have an application that I can download from the Apple Store, and then I can say, okay, this application contains Firebase that allows, the developers to collect some information, or contains libpng to deal with images, is something that can tell me who has access to some of the personal informations that I'm granting the application to have access to. It also allows me to say whether the application is malicious because of a third-party library it contains. Or it also allows me to understand whether the application is vulnerable, again, because of a vulnerable component that it is including. So just these three questions were already interesting to me, and I thought, okay, let's try to do it on, let's try to develop this technique on iOS. Now, the three questions that I showed you in the previous slide are very related, but actually require techniques that have a different level of complexity. So let's start with the application, with the question that says, who has access to my personal information? So I may phrase it as, okay, is it just the developer of the application? Let's imagine that I'm downloading Instagram on my phone. Then is the information that is accessed by Instagram only available to Meta, who is developing the application, or to other third parties? And in this case, I mean, if I want to answer this question, it might actually be enough to identify what is called the boundary between the application code and the third-party code. Okay, so I just want to know whether there is something else in the application. Instead, if I want to answer the question, does the application contain some malicious library, then I really need to understand, I mean, beside identifying the boundaries, I really need to name what are the libraries. So I may need to know, okay, this library looks like Firebase, and this other library looks like whatever fishy library. So why is this important? Just to give you a motivating example, back in 2019, Cam Scanner was, which was a super popular Android application, was banned from the store because at some point it was including a malicious application with advertisement. So Google banned the application from the store, and basically the application that was super popular suddenly dropped in the number of users. So with this, I mean, being able to identify the library that the application includes would allow you to actually identify these kind of issues. Slightly more complicated case is whether you want to understand whether a library is vulnerable, and as a consequence, whether it makes the whole application vulnerable. Because, I mean, beside the fact that you need to identify the library, you need to name it, you also need to identify the library version. Because once you find the vulnerability may affect only a specific version or just a range of releases. So when you analyze a mobile application, you do not only want to be aware that it contains libpng, but that specific version of libpng that you know that it's vulnerable. And this is actually a real case study. It's a real case that happened in 2016. with indeed the libpng, where Google was actually warning all the developers of Android apps, saying, hey, you should be updating this, this library because we know that it's vulnerable. So update it to the fixed library as soon as possible. So, okay, so we have it clear why it is important to identify third-party libraries in Android, and same reason why it would be in iOS. So we said, when we started thinking about how to implement it in iOS, we said, okay, let's look at how people did it in Android, so we can more or less have reuse the same ideas. And in Android, there are basically two classes of approaches to identify third-party libraries in a mobile application. The first one is called a cluster-based, where the idea is that the technique collects as many applications as possible, and then it looks for elements, specifically classes, that appear multiple times in different applications. So the intuition is, if you see the same class over and over in different applications, then you know that it's likely to be a reusable component. And also you could use some more advanced techniques, like you could see what classes are calling which other classes, and with the call graph, you kind of have an idea of what are the related classes, and you could actually form clusters of related classes. And with these techniques, you could identify clusters where each cluster would be a third-party library, where the good thing is that in order to identify libraries with this kind of technique, you do not need to know, you do not need to train a model, you do not need to know the third-party libraries ahead of time. You just identify these clusters and you know that each cluster is actually a separate library. But on the other hand, on the downside, you know that you cannot name a library. So you just know that this is a library and that's it. Then you would know, you would need to go and manually give a name to the library. A different class of techniques is what is called a fingerprint-based technique. That is, I try to collect as many libraries as I can, for instance, Firebase version 1.2, libpng, blah, 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 and I build what is called a fingerprint of each of these libraries that I can access to. And with this fingerprint, that is a way, like a set of features that allow me to identify this library in a unique way, I then go and analyze the mobile application and look for these features. And if I find these features, that I know that it's that library that I've been analyzing. So this basically has the converse advantage, features. That is, the good side is that once you identify a library, you know what library it is because you know the fingerprint and you know what library that fingerprint belongs to. But on the other hand, you need to be aware of a library before you can actually identify it. Or said in another way, you need to have a fingerprint of a library if you want to be able to find it in an application. So when we went for our approach, we actually decided to go for a fingerprint-based technique. So why did we go for this with libkit, that is our prototype? Well, the main reason is that we actually saw an opportunity that we don't have in Android. And it's actually that in iOS, you actually have a repository of libraries, like a huge repo where you could actually find all these third-party components. So given that you have this single entry point that collects all these components, then we said, okay, let's go for the fingerprint because we can actually analyze all the components that we find in this repository and build a fingerprint from this. And specifically, this was the Cocoa Pods repository. Now, in just one slide, how does this Cocoa Pods repository look like? So each library needs to be declared as a pod, using the technical term that is used in this repository, that actually declares the name, the version of the library, and then a bunch of other things. And this information can be used by an iOS application by declaring in a file what are the pods that are needed. In another way, the application says my test application requires Firebase version 4.7.0 in order to work. So then when I build my application using Xcode, what happens is that Xcode goes to the Cocoa Pods repository, downloads Firebase with all its dependencies, and then builds the whole thing. So it's actually a nice way of dealing all the dependencies. Now there are a couple of things, though. You see that each library has a set of what are called subspecs, which are basically sub-modules of the same library. Meaning an iOS application developer, rather than installing the whole Firebase, can decide to just use a specific module of this library, okay? And then when I get this library, I not only get the library, but I get all its dependencies. So when trying to build the fingerprint of this is already a little bit complex because it's kind of hard to get the library alone, but you actually get the whole library plus the dependencies. But you also need to think about the fact that a developer may only want a specific submodules and its dependencies. So when you need to build the fingerprint, you need to take this into account. What we found also is that there are lots of vendored libraries. So what does it mean? It means that lots of libraries that should be declared as dependencies are not declared like this, but are rather taken and completely included in the repository of the source code. So basically, you do not see the dependency in the JSON file, but the dependency is there because the code of the dependency is actually there. We also found lots of clones and small variations of the libraries in Cocoa Pods. Again, how do you consider them? Are they exact clones or slightly different applications? And then another complexity was these libraries could be deployed and distributed in different ways. So it could be distributed as a source code, or it could be precompiled. It could be precompiled as a framework, or they could be statically linked in the main binary, or it could be dynamic libraries and therefore appear as a separate executable. So this was like the first challenge. The second one was about binary analysis. Okay, the idea was, okay, let's take the libraries, let's get the executable, analyze the binary so that we could extract the list of features to get the fingerprint of this library. But again, regarding simply analyzing the executable code, we saw that it was actually challenging because within the same mobile application, within the same library, you could find many executable files. Because ideally, the app code of an application could be part of the main executable and would be like a separate file, and then each library would appear as a separate executable file. But in practice, what we noticed is that many of the third-party libraries and the dependencies are statically linked, so they basically end up all in the same main executable. And again, the problem of vendored libraries, again, they all end up in the same executable file. So again, we cannot assume that we just take one file, one binary file at the time, and think that this is a separate library and then try to identify it. So things can be mixed and not. Then came to the issue of extracting features. So what features do I want to extract to represent this library? Again, so you can think of features as anything that you can get from the executable code. This is clearly not as easy and not representative as Dalvik bytecode in Android. But there is also another issue, is that in iOS, you need to think that many of the applications are developed using many different programming languages. So what you actually obtain as a macro file executable may be produced coming from many different programming languages. So this is the result of a study that we did on the whole Cocoa Pods ecosystem. And we saw that even in 2022, the most popular programming language for libraries was still Objective-C, while Swift, even if it's like the official now language for the iOS development, is taking over, is not like, not nearly, I mean, as prominent as Objective-C. But I mean, we can see that there is also a significant amount of C and C++, and we found also 63 other programming languages, and many of them I never even heard of, okay? There is also another thing. Even if you build something, even if you have a way to extract features on executable code coming from Objective-C and Swift, for instance, then in practice you cannot assume that what you see in the source code is exactly what you have, you would produce the same executable code. In another way, we had to think of features that were representative enough, but were okay with the fact that different developers could compile the library code in different ways and therefore produce very different executable code. Then, given all these problems, then comes, well, now that I have my database of fingerprints of all the libraries, now I need to get to how I analyze an application. So in a similar way, when I have an application, I want to get the binary and extract the features to then match these features on my fingerprint database and then be able to identify what library this is. So what did we do in practice? And let me be very fast on this because I'm running out of time. So we had to, so in order to analyze iOS applications, what we had to do was to collect applications and then install them on an actual iOS device, decrypt the application, and dump the executable code that was in memory. This is because basically the iOS applications come encrypted with the user's key so that you do not allow applications to be shared. What we did well, we analyzed 86,000 entries from the Cocoa Pods database, and as features to represent the libraries and then to look for these features in the applications, we actually used features that we could find in the binary code that represent the class name, the list of method names, the list of instance names in Swift, in the executable code that is produced by Swift and Objective-C. And with all these features, we computed a SIM hash to get a class fingerprint, and we represent the library fingerprint as a set of class fingerprints. Now, maybe if I have just one more minute, okay? Then let me show you all the technical details. I mean, you can find in the paper, and I'm happy to tell them later. But in essence, what we did then was to actually analyze, evaluate how good our approach was on a ground truth of 95 applications for which we knew exactly what libraries it contained, and we could see that the results were pretty good for, I mean, considering only the libraries that were in our fingerprint database. However, we saw that roughly 37% of the libraries that we find were not in the database. So we couldn't really identify them in the application and couldn't really find them and couldn't really name them. Let me skip this. We also evaluated how good we were at detecting the library version, and we actually found good results. And let me conclude with this, where we actually tried to apply the technique on over 1,000 libraries, applications that we could get from the Apple Store, where we could identify 47 library versions in total. And we could see that the majority of these libraries that we could find are actually technically linked or vendored. So these are hardest to actually identify. And we could see that we could find a median of 25 libraries in each application, where we could even find a case of a single application that contained over 100 libraries. So again, the information that this application has is shared with a lot of third parties. And we see that the biggest player in this third party libraries is actually Google, because we could see that the Google mobile ads is actually the library that was most prevalent in our data set. So to conclude, I have been telling you about all the Android research that I've been doing, all the iOS effort that we have been doing in the last 2.5 years. So this is the time that it took us to develop all this and to have just one single paper. So to answer the question and conclude, why do all researchers work on Android and kind of leave iOS out? Well, the question is simple, because it's very, very, very hard to work in this domain. Every single step is a challenge. However, I do encourage you, if you work on mobile apps, to actually look at this domain. So if you are crazy enough or a masochist and want to switch and try the pain of working on iOS and willing to collaborate, please come and talk to me. I'm very happy to share all my knowledge and share all the tooling that we have been doing so far. Okay.
Hello. First of all, thanks for sharing your detailed and multi-year research experience with us. As most of your analysis are based on static analysis, either permission analysis or third-party library uses. So can we conclude this key by doing only static analysis of particular mobile app, we have a good confidence level, or almost like F1 score is showing 87.4% confidence level, or app is trustworthy without doing dynamic analysis? Can we conclude this?
Well, I think, so the reason why we have been going for static analysis is that it's way easier. And dynamic analysis, it's true that there are many techniques that do this, but in practice do not have a very good coverage of the whole behavior. And anyway, there are some things that you still need to do manually. Like many of the mobile applications still need like a login or kind of things that require some kind of human intervention. So, I mean, I would love to do more studies using dynamic information, because that really gives you the ground truth of the actual behavior. But in practice, I think it's not really reasonable to do it on a large scale.
Because it takes time and resource intensive also.
Yeah.
Yes.
Yeah.
Thank you.
But I mean, it would be the right way to go, although it's...
Yes, this was very interesting and a lot of knowledge you shared. Thank you for that. I have a question regarding what I attended the Black Hat and DEF CON conference last year in Vegas. And one of the themes was that when you compared Windows systems and Mac OS, that more and more malware comes now to Mac OS. Not because one or the other system might be more secure, but just because the numbers are rising. So Mac OS is getting more market share. Do you see a similar thing here happening with iOS versus Android?
That is my, so I don't have numbers because we haven't gone this far, but this is my intuition as well. And the reason why nobody's really talking about the security issues with iOS is that, I mean, nobody has looked into this very deeply. And, but yeah, I totally agree with you. So with the growing number of users, then it is way more worthy to develop malware for this kind of platform.
Yeah, my name is Sai. Thank you for the talk. I joined halfway through, but I could try to condense. So I worked on some parts of mobile development with Android open system platform, where you can write your privileged app and mother app.
Yeah.
So I was looking at when we tune the open system and give it to most of the manufacturers for Africa, India, and some places where they don't want to live on the original Android version. These problems will become a key aspect there. So these tools can also be like they can work as a vulnerability detection tools for those apps. Is it something an end user can perform by routing it on those ASOP OS and detect by themselves?
Yeah, because actually we don't I mean, all the Android stuff works on a normal device. We actually analyze the application without analyzing the iOS.
Okay.
It's a different thing for iOS. For iOS, we actually needed to jailbreak the device to be able to install it and then decrypt the code and dump the memory. So we had to work on a jailbroken device, but that was the only thing. I mean, it's really much hard even to get the executable code. Then in Android, you just take the APK, you unzip the file, and then you have the Dalvik bytecode there.
So last two questions in interest of the lunch that is overdue.
And then I'm here for the rest of the day until the end of the conference, so happy to take questions offline.
Hi, thank you so much for the interesting talk. I think I have a question on the binary analysis and the library dependencies itself. So I think most of the library dependencies don't exist in isolation, right? So if you try and upgrade one of the vulnerabilities to a different version, all the other libraries actually break down. So did you have to successively upgrade every version, come to a fixed point, and then generate the fingerprint, or was...
So yeah, so in order to build the fingerprint, what we did was we had like a fake application that was declaring a dependency of either the whole pod. And in that case, we were getting the whole library and all the dependencies, and then all the submodules with the different subdependencies. And so depending on when we were running this build command, we were getting a specific version of the library that was, well, depending on what was specified in the pod. So, like, if we were rebuilding the database now, we would have very different fingerprints. So this is like something that you should be continuously doing to answer your question.
Thank you so much.
It's a challenging thing to do.
Yeah, thanks for sharing the insights. So my question is, what's your view on the analysis of these mobile applications with respect to native applications as well as non-native mobile applications? Because native applications, since they are like powerful, they have access to the underlying frameworks of a particular platform, and with like great power comes great responsibility. So is there any specific observation throughout your analysis?
I mean, my take is, so I always work on the native applications, but all the frameworks that are out there, like, for instance, allow you to develop web applications that work on different platforms, are out there, are getting more and more popular, and are worth looking at. So I never did any analysis of those, but it's definitely worth looking at because many security issues may actually arise. So I never did it myself, but I think it's really worth shifting the focus there because they are more and more used by developers because they are convenient. So with just one application, you can, I mean, deploy on multiple systems. And yeah, in a way, you rely on the framework for development to deal with all the security and privacy issues, but yeah.
Thanks.
I think it's worth looking at.
Okay, thank you, audience, for all the good questions, and thank you, Alessandra, for the excellent talk. And now I request Raghavan to please hand over a token of thank you from our side.
Thank you.
Thank you for coming all the way from Madrid.